Welcome to the lecture Machine Learning, and in this video we want to talk about k-nearest neighbors. So let's say I give you a specific data set, and here this is a very famous iris data set, and I ask you to learn a classifier which can predict the specific species given in this data set. So Certosa, versicolor, and virginica. So these are three different kind of classes which are in the data set. So this is your task, and as you learned in the last video, it's a supervised learning task. So you have some data set, you have given ground truth labels for every instance, and we want to learn a function which maps from the input domain X to the output domain, which are here these three classes, Certosa, versicolor, and virginica. So S, VE, and VI. So this is what we want to learn here. So the first you should always do in machine learning, or in general in data science, I would say, is that you should look at your data. Okay, so if I give you a bunch of data, please first try to illustrate it, visualize it in a specific way. The easiest with some kind of scatter plots. So here what you see is always like one dimensions of the input. So you see you have like 1, 2, 3, 4 different dimensions, how this data is characterized, right? The sepal length, width, and petal length and width, right? And we can, for example, do this kind of scatter plot, which always plots one dimension with the other dimension, right? So here you see the other dimensions, every dimensions with respect to every other dimension. On these terms here, these are scatter plots. And what you see on the diagonal here are just histograms of the specific feature, right? So you see here the feature, which is here like the sepal length, right? And you see here a histogram, how often does a specific instance occur with this specific feature. So let's say here, right, let's say this is like 4. You see in class blue, you have a couple of instances which have the value 4 for sepal length, a bit more like 5, and so on and so forth. And you see already that, for example, the red instances, class 3, they are slightly higher usually in this feature. Okay, or here, for example, if you look at this feature, and here you see the histogram, you see that the blue, for example, already stands out quite a bit. Okay, so this is the first you should always do, right? You should try to visualize your data, and then you already see some patterns that, okay, here apparently the blue class stands already a bit out, and here you can also already see that red and green are a bit separated. So there might be hope actually that you can try to find now a classifier which can distinguish between these three classes if I even give a new data sample. Okay, so let's do this in a bit in a simplified scenario. Let's say let's look only at 2 features. Okay, so we have here pick 2 features, which was here this setting, right? And you see already again these instances are the blue ones, here are the green ones, and here's the class 3 red ones. So how can we now learn a classifier if we get a new instance, right? So let's say I give you a new input instance with 2 features. Let's say it's located here, right? So the first feature is around this value, the second feature is around this value. So how can we now make a classification decision? How can we now say, okay, is this class blue, green, or red? And the core idea of a Knn classifier is that we just look at the surrounding points, right? So we see essentially, okay, what other data instances have we seen so far which have similar characteristics? And similar characteristic means similar features here, right? So for example, all these here, they have also features around this value and this dimension, and features around this value and this dimension, right? So these here are the similar instances having similar features. And since these are all mainly blue, it might be a good idea to say that this sample is also or belongs also to the blue class. Okay. So similarly, right, if you now get, for example, a new object which is located here, right, so the feature values are accordingly here like 3.5 and 1.5, then it would be a good idea to classify this as green. This belongs to class green. Okay. So you see, based on the simple rule, looking at your neighbors, you have found a way to say, even if I get a new instance, any new feature combination, so to say, right, you can either say it's one of these classes here. So you do this by looking at the neighbors. And that's the core idea of this Knn classifier. And let's start with the simplest one of this, which is so-called one Knn classifier, one nearest neighbor classifier. So formally how it looks like is the following. So we have first our training data, as you already learned from supervised learning. So we have here our input instances X, which could be like a two-dimensional input, as we have seen. Actually, it's written, right? So here it could be like d-dimensional input. Let me just remove that here from the slide. Could be d-dimensional input vectors, two-dimensional in the previous slide. And don't forget about it, we have a supervised learning setting. So we have also given the corresponding class labels for these training instances. Okay, in general, we could have C classes. In the previous example, we had 3 classes. Okay, so this is what we have. And then what we just need for a 1 and n classifier, or K and n in general, is we need to do the following steps. So first of all, we have to define a so-called distance matrix, which measures which other instances are similar to myself, so to say, right? So here we have to define what are the instances which are close by. So often we are using, for example, Euclidean distance. Then once we have defined this distance, we can compute the nearest neighbors, right? We can compute this neighborhood. And then we see here in this 1 and n example, we see what is the closest neighbor, and we label the new instance with the same color, with the same class, okay? So here, for example, this would be the closest, it's blue, so we label it as blue. Here, this is the closest, it's green, so we label this instance with green. And indeed, it is not here restricted to classification, it also works for regression, as you can imagine. If you just see what is the closest instance, right, what is the most similar person, to myself, for example, and then I can also use it for regression. So let's say the task is again to predict the income of a person. Of course, I can look at the most similar person to myself, and then the person's income, whatever he has, is also most likely my income, for example. Okay. So this works for classification as well as for regression, because we essentially just take the target of the instance which is closest by. So how does it look like for an abstract example? So let's say here again we have some two-dimensional feature space, x1 features, x2 features. So this is now just some toy synthetic example. You see here like our training data. So here these are the ground truth training data from class blue, here some from class green and some from class red. And what you see here is the classification decision we will make for a specific instance. So let's say we have here a specific instance. It arrives, right? That's a new test instance. We see what is the closest other instance, here blue, so this will be classified as blue. Same here, right? If you look at this point, the closest one will be blue, so it will be labeled blue. And here, for example, if you look at this point, the closest one is red, so this is red. And this then gives us these regions, these decision regions, so to say, how every instance in the space, every unknown instance so far will be classified. So all instances here will be classified as red, all here will be classified as blue, and so on and so forth. So these are, so to say, the decision regions. And just one term we will encounter more often are the decision boundaries. So here, the border, or the boundary as the name says, these are the decision boundaries. This is essentially the case where we flip between two different classes, for example, or where we are undecided. If we're exactly here on the boundary, we are somehow undecided whether it's red or blue. Okay? So this result, what we get here from a 1 and n classification, more or less corresponds to a Voronoi tessellation of our space here. Okay, so we have here our training instances, and we do some kind of Voronoi tessellation to find these regions here. And as you already see in this plot here, this indeed leads to very poor generalization. This means, for example, that if you look at this here, right, there's one instance which is classified as red. Well, it's not classified, it's labeled as red to be specific, right? The training data says it has a label red. And what happens then is that here, this tiny region here will also be classified as red. So if you're unlucky and there arrives a new instance exactly at this point here, it will be classified as red. Even though we see that here it's actually located in this vast space of blue instances, right? So this tiny red instance we have in our training data essentially makes a prediction here in this region more or less like unintuitive wrong, meaning we do not really generalize. This noisy example here makes our prediction bad. Okay, so a 1 and n classification is not very robust in this sense. It does not really generalize well, and of course generalization is what we want in machine learning, right? Don't forget about the function we are trying to learn here. This should generalize well from new to the classes, from new instances, right? But it's unlikely that, for example, this new instance here is really red. It's just that we were unlucky that our training data had here one specific instance. Similar here, for example, right? We are just unlucky that the training data is not perfect, that it's noisy. And then if a new instance arrives here, this will be classified as red, but actually it would be more likely to say it's green, okay? So 1 in n is not a good idea. That's a simple conclusion. So what we can do instead is we do a so-called Knn classifier. Knn classifier simply means we do not just look at the closest neighbor, but we look at the k closest neighbors, right? The k most similar people around me, so to say. And then I, for example, can take the majority vote, okay? If we actually go back to this plot here, so let's say a new instance arrives. So let's say here this new instance arrives, which could be here, right? We look at the k most similar ones. So let's say here these here are the k most similar ones, these 4 instances. We see that 3 of them are blue and 1 is red, for example. So we could say this new instance should be classified as blue because the majority of my k neighbors is blue. Okay. So that's a simple idea, and here it's actually formalized. So if you, for example, have a new instance X, a new input instance, a new test instance, you look at the k nearest neighbors, here denoted as nk, the neighborhood, okay, the k closest instances, and then your prediction you are doing is essentially you take the majority vote as a simple choice, or you can look at it already from a probabilistic perspective. So what I mean with this is the following. So we have here the probability that the class label, so y is the class this object has, corresponds to class C, right? So let's say the first class, given like that we have here our input X and the number of neighbors K we are looking at, we can essentially just look at the fractions we have here, okay? So what I mean with this is the following again. So let's say you have here an instance, you look at the neighborhood. So let's say here you have a red instance and I don't know, 3 blue instances. Then the probability for y being blue equals to 3 out of 4, and the probability of y being red equals to 1 out of 4. Okay, so in this tiny example here. And this is exactly what is illustrated here. So here you have the indicator, whether the label is red or blue. Here you sum over the full neighborhood, and here you just normalize it to make it a proper probability distribution, because these terms here, they should sum up to 1 to make it a proper probability distribution. Okay. So this is like a bit of already like a probabilistic interpretation of the Knn classifier, where we have here like these fractions. And then, however, what I said is that usually you just take the majority vote. So you take the class, the argmax of the class which has here the highest probability. Okay, be careful here. Here it's the argmax, right? We are not looking for the largest probability, which would be 3/4, but we are looking for the class, so the argument which maximizes this function, which would be blue here, right? So we check blue 3/4, red 1/4, so the output will be here blue. Okay, blue is a class which maximizes the probability, the argument. Okay, so here blue would be the return result. So of course now you might ask, why do I actually compute here this probability? Actually, you don't have to do this if you really go with a majority vote. Of course, you can avoid dividing here by 4. You can just look at the absolute numbers. So 3 is larger than 1. So you just return blue because this is a majority class. Okay. But here I just wanted to introduce this because in the remaining of the lectures, videos here, we will talk about a lot of probabilistic approaches. So it's good to already have this understanding about this probabilistic kind of interpretation of machine learning, where you now essentially compute the probability that the class is blue or red. Okay, so given our input data, given the parameters k here in this case, we want to compute the probability of the class label, for example, that the class label is a specific class. Okay, good. So that's the core idea of a Knn classification. You can use a majority label. You can actually, so here you see what I just said. So you can actually also just generalize it to some kind of a weighted setting. What I mean with this is the following. So let's say, again, you have here a new instance. And let's say you have here now an instance which is red, which is very close by. And then you have here, let's say, again, 2 blue ones, which are quite far away. If you do a standard majority vote, let's say here, we have here now this neighborhood, right? You do a standard majority vote, then of course this would now be classified as blue because we have 2 blue and 1 red. But you could also argue because this red is so similar to the current test point, red should have a higher influence on this, right? Because this is really so similar, it's actually more likely that this is red because these 2 blue ones are actually quite far away. Okay, and this is essentially then just a generalization of the previous one. So we do a weighted majority vote. Not every sample, every training instance in my neighborhood has the same importance. In this case, it would be 1/3, right? But we also take into account the actual distance. The closer by, the more important. So if you want to formalize it, it could look like this, for example. So again, we compute first of all the set of k nearest neighbors. So in this plot it was 3 here, right? We then also use a specific distance, which could be like the Euclidean distance, for example. And we give every instance a weight which is inversely proportional to the distance, meaning if the distance is small, this is small, the weight becomes large. If the distance is large, the weight becomes accordingly small. Okay, so the closer by, the more important. And again, what we do is if we want to compute the probability of class blue, we more or less like look at the neighbors which are labeled as blue, right? So it's again this indicator function. So if the label of my neighbor is blue, this becomes a 1, right? So we are summing up these weights for all the blue neighbors to get the blue score, and we are summing up again all these weights for the red neighbors, and then again get a score. So again, if we have this probabilistic point of view, there's one tiny detail missing. We have to normalize again. So if you look back at what we have seen here, right here we normalized by 4 because we had here 4 instances which are all equally important, right? Everyone has a weight of 1 divided by 4, so to say. Here, everyone might have a different influence, a different weight. So to make sure that these terms here sum up to 1, right, because it has to be a proper probability distribution, we have to find this normalization constant, which is just the sum of all weights. Okay, so this is how you can think about it. So I'm computing the weight to everyone. So here this one gets a large weight, these two get a small weight. We sum it up, we get the overall weight, the overall mass, so to say, and then we just have to divide by the overall mass here to make sure that this later on sums up to 1. Okay. So that's simply the core idea. You see what we need here is we need to have this distance function, okay, which measures how close are the other ones to myself. But we anyway need this to determine the k nearest neighbors, right? Remember, this is the one requirement for K and N classification. We need this distance function to figure out what are the closest instances, right? So one tiny information here. So what could happen in principle is that we have an instance xi which is exactly at the same position as the test instance. So they coincide, meaning the distance would be 0. Of course, then this here will not be well defined. So what you can of course do is you can add here, for example, some tiny epsilon value to make sure that you're not dividing here by 0, but you're always dividing by some proper number. Okay, so that's just some tiny technical detail. But overall, this just gives a weighted majority vote to take into account like also the arrangement, so to say, in this space. But otherwise, the principle is more or less the same. Okay, and then as I already said, we can of course also do K and N for regression tasks rather easily. Again, here let's look at the weighted setting, for example. Again, we compute first our nearest neighbors. That doesn't change here. Let me make actually an example. Okay, we have here our point. Let's say we have here the set here, and then we have now a regression setting. So remember, regression setting, we don't have different class labels, but we have like numbers attached to everyone. So let's say this is 8.1. This here is 7.6, and here another one which is 1.2, for example. So these are our training instances, and it's now a regression scenario, right? We have here like continuous targets, no longer red, blue, green, but 8.1, 7.6, and 1.2. Okay, and what we can just do is we compute here the nearest neighbor set. Here again 3. We do, for example, this weighting according to the distance. We can do this, we don't have to do this. But most importantly here, this is the most important part. We take the actual label, which is now like this continuous version, right? We take here the actual numbers, and we just more or less do a weighted mean. Okay, can do a standard mean, we can do a weighted mean according to these weights. But essentially, we have to take here the actual target value, or we can take the actual target value, and then we get here our prediction. Okay, so be careful again. If you have here a weighted version, you have to make sure that this is properly normalized, right? If you just do the standard mean among these points, this would be, of course, again 1 divided by 3, and this would be here then disappear, or 1, right? If you have a weighted version, you have to make sure that this is properly normalized, otherwise you're not in the correct scale again. Okay, good. But as you see, it's straightforward here to generalize these to a regression scenario. So Knn in general is extremely flexible, classification and regression. Okay, so here you see again the main difference. Y has become a real number, and we do a weighted mean. Okay, so how does it now look like? So compared to this Knn classification, we get a much nicer result. So the same plot, same data as before. We have two features here. We have here our training instances, which have the corresponding class label. And you see here the difference here was the red instance. And before we have seen that around this red instance, it was classified as red. Now, of course, this is classified as blue because in the majority, the majority of the neighborhood is blue. Okay, so this here now is also blue, which means we generalize better. Same here, right? It's still classified as blue, or here it's classified as green. So we get rid of these tiny regions, which essentially are not desired, which essentially lead to bad generalization. Here now we have get rid of it. We have now nice regions. Of course, it's not perfect, right? Here's still a bit of a blue, right? But we have much better generalization performance. If you, for example, again compare it to the Knn, right? So here are these tiny regions. Here they disappeared because we look at a larger neighborhood. We have a larger support, so to say, to make a decision, right? We get more evidence to make a decision in this region. Okay, so this is the core idea of a Knn classifier, Knn regressor. Of course, one follow-up question you should ask yourself now is, how do we now pick a corresponding K, right? Because this looks quite okay-ish. This looks not too nice, right? Here you have all these kind of tiny regions. What K should we pick? 3, 20, 1 million? We don't know yet, right? So just as a question for yourself, and take your time to think about it for a second, so you can pause the video. So what will happen if the K we are picking here is equal to the number of data instances we have in our training set? So let's say we have 100 training instances, and we pick K equal to 100. So what will happen as a result here? Think about it for a second. I will take a short break here, and then I will give you the answer. So if you use K equal to the training size, what will happen is essentially that every point on every possible position, you get the same prediction, and you get the prediction corresponding to the majority class, assuming you do this majority vote version, right? So because the majority vote just essentially takes the largest class, and since K equals to all instances, in every step, you look at the full training data, and the prediction will always be the same. It will be the largest class, okay? So this, of course, only holds if you do with the majority vote. If you go with the weighted majority vote, of course, it can look again different. But in general, of course, picking K so large doesn't make any sense, right? Because you just would look at the full data set all at once. So, of course, that's not the best idea. So you already see now that there's some kind of like trade-off or variation, right? If you have K very small, it's not good, right? If K is in the middle, it might be good. If K is too large, it's again bad, right? So small is bad, very large is bad. Somewhere in between it has to be. But how can we now pick this in a more principled way? And one usually performed way is to do a kind of splitting of your data. And this is a very fundamental principle in machine learning. So usually what you do is you take your data, your training data usually, which you have at hand, and you split it actually usually in 3 different sets. One is a so-called training set, which you actually use to train your model. Then there is a validation set, which I explain in a second. And then there is an actual test set, okay? So here comes one important point. So in machine learning, we try to generalize to unseen data, right? That's the actual goal. Right, we want to see how this also behaves for new images, for example. The drawback is for really unseen data, we don't know how our model actually will perform, right? Because if we get a new image, there is no label attached to it, right? We don't know what this actually is if we don't, as a human, don't always look at every image, right? So how can we actually then evaluate the performance of a model? So the point is that in machine learning research, and also like if you want to deploy it, you always have to take apart some test set. This test set is essentially like your proxy for really new data, so to say, right? Because for the really new data, you don't have a label. You have to use this proxy of a test set, which comes from your labeled data, which you then at the end of the pipeline can use to analyze the performance of your model, okay? So what is important to note for the test set is that this test set should be used only at the very end of your model performance evaluation. We talk about this later on in much more detail in the good data science practice in the next video here. But important is that you cannot use the test set to do any kind of tuning of your machine learning pipeline. So this test set, and this really acts as a proxy for the unseen data, you're only allowed to touch it once, because also the new data you're getting tomorrow, you will only see once, namely tomorrow. Okay, so this is one point I just wanted to mention here already, but we will see this later on in much more detail also in the good data science practice part. So back to the actual question. So we want to pick a reasonable case. So how do we do this? We do this by doing these kind of three splits. We have the training set, which we're actually using to train our model. Then we have a validation set, which we can use to tune our models. Okay, as it mentioned here, we can use our validation set to see, okay, this K is good, this K is not so good, and we pick the best K based on the validation set. Okay, so the validation set is more or less useful for tuning your model, tuning the parameters of your model. We see this later on. There are many other parameters which models might have. Here it's a K and K and N. But the validation set is used to tune your model, which you are training with the actual training set. Okay, and once you have trained all this, at the very end, you measure the performance on the test set. Okay, so this is essentially the standard split. And I mean, there's often a question, how do we pick these splits? I mean, there's just some different rules of thumbs. You could, for example, say this is 80%, this is 10%, and this is 10%. But this, of course, depends on the specific scenarios, but this is a rough guess how these should look like. So important, of course, is that this training set is not too small, because if it's too small, we don't have enough training signal to actually train our machine learning model. And so we have to have enough samples here. But likewise, these should also not be too small, because otherwise this evaluation or this tuning, right, as mentioned here, this also then doesn't work if it's not well represented. One other point I want to mention here, and this is also something very important, is if you, for example, look at a classification scenario, right, where you have, for example, different classes, blue, red, and green, what you want is that in all these different kind of sets or subsets of your actual data, every class is well represented, okay? So meaning, how do you find actually this kind of splits? Of course, you can think about just some random selection, right? You have your full data set and you randomly pick 80%, and then from the rest you pick randomly here the validation, here's the testing, right? So this is just some random sampling, okay? So you can do it really just randomly. What could happen, and this is a small drawback, is that if you're unlucky, that for example in the validation set, because it's rather smallish, there is no class blue. So the validation set only contains red and green. And then, of course, this is not a good validation set, not a representative validation set to really do some kind of parameter tuning. Okay. So what you want usually is that all these kind of different subsets, that they are representative. They should represent your overall population. And what you then can do instead is so-called stratified sampling. Stratified sampling means essentially if in your overall population you have 80% red and 10% blue and 10% green, I make sure that also in the corresponding subsets I have the same proportion. So 80% red, 10% green, 10% blue, for example. Okay. So the proportions in the overall subset are also preserved in the corresponding subset. This is known as stratified sampling, and this is potentially what you should do specifically if you have classes which are very small, right? If you have a huge class imbalance, so you have one class, for example, which only have a small amount of instances, you want to make sure that this class is also represented in all these different sets. So stratified sampling might be a good idea to find these three splits here. Okay, good. But again, we will talk about in a bit more detail in the next video. But since this is very fundamental, I wanted to mention it here up front, but please take into account this general principle of splitting it into these three pieces. Good. So how does it then look like? So if we now look at, for example, the Knn classifier, right? So we have now our two different data sets, for example. We have our training data set and our validation set. What we can do now is we can play around with the number of neighbors, okay? Meaning, for example, we can train, whatever train here means for a Knn, it's not really in training, as you might have noticed, right? But let's say we construct a Knn classifier where we use 5 neighbors, and then we can evaluate the performance on the validation set, which, for example, leads to this kind of accuracy. Accuracy we talk about in a second what this means. But we need some kind of measure how good this result is, okay? If we, for example, pick 30 neighbors, we see that the performance on the validation set is not so good. As we discussed, if k is too large, we essentially like over smooth and we just predict the majority class, okay? So we see here the issue, too large k leads to bad performance, rather smallish k might also lead to bad performance. Somewhere in the middle, we have the best performance, okay? And then using this plot here, we can now decide, okay, let's use here where the maximum is, let's use this k, for example, k equal to 7. Again, very important. You evaluate here with the validation set. You see it here, validation accuracy. We have our training data to form the classifier, right? And for Knn, it means we have here our training points. And then we take the validation set, and every instance from the validation set is looked at. Is it correctly classified? Yes or no. Next one, is it correctly classified? Yes or no, right? And then we can compute some performance measure, accuracy, and we see how this varies with the different parameters we, okay? And that's then our choice. And then, again, we discuss this later, but once you have now made this choice, k equal to 7, you can now finally report the performance on the test set, and this is the number you can show your customer to say, yes, our approach works. Okay, good. But here we use it, for example, to picking the corresponding parameter based on the validation set. So as I said now already a couple of times, to do this kind of parameter selection, so what is the best parameter, we have to have some performance measure, measuring how good our classification result is, okay? And you can do this in various different ways. I show you here a few. So one fundamental term you should have heard about is a so-called confusion table, used for classification evaluation. What is a confusion table? Here it's shown for a so-called binary classification, meaning we have 2 classes. We see here, on one hand, the true condition. True condition means how is this instance labeled in our training data. And remember, since we want to evaluate the performance of the validation set, we have the label given for these instances because the validation data comes from our labeled given overall training data. Okay? So for these instances, we have the label, and this is what is known here as this true condition, which could be class 1 or class 0. Okay? And then on the other side, we have the predicted label, okay, which could again be class 1 or class 0. Okay, we can predict it correctly, or we can also predict it incorrectly. And then there are these 2 different notions, right? We have the true positives, so it's true. It was labeled 1 and it's also predicted 1. We have the true negatives, meaning it was labeled as 0 and also predicted as 0. And then we have the false negatives and false positives. Okay, you also see it again here in the illustration, these 4 different cases. Of course, what we want is we want these to be high, right? We want the true positives and the true negatives to be high. And of course, we want to have the false ones to be small. So you see it here. These are the correct predictions and these here are the wrong predictions. So this is a confusion table, and you see that this confusion table is compromising like 4 terms, right? We have these 4 terms, but what we need here is somehow like a single measure because we want to take the maximum value. And based on these 4 terms, indeed, there are various different measures how we can now report the performance. Here's just an overview. On the previous slides, we, for example, have used the accuracy. What is the accuracy? The accuracy is simply the correct predictions, right? So we have here like correct the true positives and the true negatives, divided by all instances in the validation set, for example, right? So these are here just simply all instances, validation instances, and these are the correct ones. So this is the accuracy. And this is one standard measure one usually uses, because this is like just the ratio of correct ones. And if you see it in this plot here, roughly 94% of all validation instances are correctly classified, which is quite a decent result. And yeah, this is one way of evaluating it. But then, as you can imagine, there are many other measures, like precision, for example, measures the ratio of true positives divided by the true positives and false positives. And it's the easiest to show it here, right? So here, this is essentially like what the classifier predicts, right? So the classifier predicts class 1 for these instances, and we are dividing this number by this one. This is a precision. So how precise is our prediction, right? Here it's class 1, predicted. How many of these are actually class 1? This is what this is telling. And then there's also recall or sensitivity, which measures some other different aspects. How many of the ones which are labeled, known to be class 1, how many of these are actually detected, so to say, right? Because we are measuring here true positives divided by true positives and false negatives. So these are the ones which are missing in our classification. So the prime example is really like disease prediction. So let's say someone has a specific disease. Of course, we want to make sure that every person who has the disease will be detected, right? So we want specifically also the recall high, right? Everyone who has a disease should be detected. So we don't want to have false negatives, which are more or less like the people which have the disease but are not detected. They are falsely classified as negative, right? But on the other hand, we also want to have a good precision, because you can easily obtain very high recall by just saying everyone has this disease, right? If everyone has this disease, of course, the recall is 100%, right? But the precision will be very small, because among this prediction, many of these people will actually not have the disease, okay? So this is actually why you also have like specific plots, like for example, precision and recall plots. So here's precision, here's recall, for example, or the other way around, however you want to look at it. And as I said, if you have a high precision, you often have a very low, high precision, you often have a very low recall. Or likewise, if you have a very high recall, you might have a low precision, right? And this curve can look like this, for example, right? If you vary some specific parameters of your model, so high recall means low precision, high precision means low recall. But if you parameterize it differently, you see different behavior. And for example, you want to have results here, right? Where you have both high precision and high recall, okay? And based on these kind of plots, like these precision recall plots, for example, there are again different measures. Some of you might have heard about area under the curve, which would be like really, as the name says, this area under this curve, for example, which is just like also different measure how to evaluate their performance. So here, it's just as an overview meant, right? I don't have to read this out all in detail. Just one last point. Very famous is also the F1 score, which is here like a harmonic mean between the precision and recall terms. Right here, it's these two terms I just talked about. Right here, it's like the harmonic mean between these. Why the harmonic one? Because we want to avoid to be in one of these extreme cases. So this term is high if both of these measures are somehow good. If one of these becomes bad, so let's say recall is 0, then of course the overall term becomes 0, right? So this term specifically wants to make sure that precision and recall at the same time are high. Sorry. Okay, so this is the F1 score, also very famous. So at least you should remember these 4 terms, because I would say these are the most popular ones used for evaluating performance of models. Okay. So one last point I want to mention here, and this is what we don't discuss in detail in this introductory lecture, but you should be careful when you have imbalanced classes. Imbalanced classes means that one class dominates the other one a lot. So let's say, again, this disease example. If you think about like let's say you have a training set, then it might be that among your training instance, let's say 1 million, only 100 have the disease, and the rest of these almost 1 million do not have the disease. Okay, so one class dominates the rest. Okay, in this case, you have to be extremely careful how you interpret these results, right? Because, for example, you can trivially achieve a very high accuracy in such models. So think about, again, let's say you have 10 instances class blue, and let's say let's make another example. So let's say 9990 times class red. Okay, so this is your training data. Many red and only a few blue. So you can easily achieve high accuracy by just learning a model which always says red, right? So if I have a model which always tells you red, these are all correctly classified, but only 10 of these are misclassified, okay? So meaning your accuracy would be already 9,990 divided by 10k, so this number divided by the overall number, and this is already close to 1, right? Because this class is already so big. Okay, so you can easily achieve an accuracy close to 1 in this scenario by predicting just the majority class. Okay, so please be always careful when using these measures. Be careful specifically if it's imbalanced, because then some of these don't actually make sense. So you can then think about, for example, having some weighted versions of these measures, right, where these instances get a higher weight, that they count more, so to say. But the pure measures, they might be not a good choice for this. So please take this into account again. And then, of course, for imbalanced data, for example, might also be useful just look at the confusion table, even though it might be a bit more expensive, so to say, to analyze, because you have all these 4 terms. Okay. But long story short, in general, you have different measures to evaluate the performance. And these measures can be used to parameterize your model. Which k do you want to pick? You pick the one k which leads to the highest accuracy on the validation set, for example. Okay, so now we have established the following points just as a recap. We know what the Knn classifier is. We know how to pick this k based on our validation set. And then finally, the only piece which is missing is what kind of distance measure do we need or do we use for Knn? Because this is the only requirement, so to say, what we need in a Knn classifier. We need the distance to find the corresponding neighborhood. Okay? And indeed, since this is the only requirement, the Knn classifier is indeed extremely flexible because we only have to pick it. So for example, if we have some kind of a vector data, what we have seen so far, right? Let's say we have data in a two-dimensional plane, for example, right? We could use, for example, the standard Euclidean distance, like the air distance, so to say, right? The shortest distance between these vectors, defined as this, as you all know. But it could be also something else, right? It could be, for example, the L1 norm, which is not here the squared of the component-wise differences, but it's just the absolute value, right? It could be the L infinity norm, which is like just we look at the dimension which has the largest distance, right? If you have, let's say, 10 dimensions, a 10-dimensional vector, we always compute the distance between two, right? And we see what is the largest. Let's make just an example. So let's say we have these two vectors, right? Let's say we have this here. Then here this would be, of course, 1 plus 5 equals to 6. And here this would only be 5, right? Because here it's a distance of 1, here it's a distance of 5. We sum it up. Here we just look at the largest one, which is just 5, okay? So just different measures to measure distances in this vector space. You can use, for example, the cosine distance, which is a very famous measure, of course, often used for text data, for example, for text embeddings. It's defined as you see it here. It more or less represents the angle, right? As you see, we are computing the angle between two vectors, and this could also be a reasonable distance measure which we can use. The benefit here is that this angle, of course, it's independent of the length of the vectors, right? You see it even here. So we normalize more or less by the length of the vectors. So it's invariant, so to say, to this length, while the other ones, of course, not. So here again, by the way, you see these other measures here. This would be the infinity norm, so the largest distance between these points in one dimension. And L1 would be, for example, the sum of these, and L2 is here this direct connection, so the length of this direct connection. Okay, so these are just a couple of distance measures. We can even generalize it further. We can use as the so-called, look at the so-called Melanobus distance, which is like a generalization of the Euclidean distance, right? So here it's formalized. So if you see, the only difference here is in the middle, this covariance matrix, so to say, which should be a positive semi-definite and symmetric matrix. What it's essentially doing in an illustrative point of view is the following. While the Euclidean distance is looking like circles, so to say, the Melanobus distance can look like this. So what I've drawn here are the so-called isolines. So if I have a query point and I'm drawing this here, so these are all instances which have a distance of 1 to the query point. Okay, so we have here the query point, the test point, and here everyone along this line has a distance of 1 to the sample. It's like a circle around here for Euclidean distance. For Melanobus distance, where of course you have this kind of covariant structure, you get this ellipsoid kind of shape. So you have here your test instance, and everyone which is on this line has a distance of 1. So you see that we allow a longer, so to say, range along this direction, while it's here closer by. Okay, so we kind of like a stretched view, so to say, on this space. Okay, so why is this a generalization of the Euclidean distance? Because if you make this an identity matrix, right, diagonal 1, everything is 0, everything else is 0, this becomes Euclidean distance. The Euclidean distance is a special case of the Melanobus distance. Okay, and last but not least, you are not restricted to use Knn classifiers for vector data, right? So we don't have to just look at here these vector spaces, but we can use it for any kind of object where we can define distances for. Think about, for example, you have text. You can look at the so-called Hamming distance, for example, or the edit distance, which looks at how much do I have to change or how many symbols do I have to change to transform one text in the other text, right? Or you can use it, for example, for graph structure data, what our group is working on, right? You have one graph and another graph, and you can, right? So let's say here's one graph and here's another graph. And once you can define a distance between these two objects, you can use it for Knn classification, right? Because I give you a new test graph, you see which other graphs from our training set are similar to it, which are the closest ones, and then I can use the principle of Knn classification. So indeed, Knn classification or regression is extremely flexible, because once we can define a distance, and we can more or less always do this, we can use this principle for doing classification or regression. Okay, so these were actually a couple of advantages for Knn classification. Now let's quickly go over to some disadvantages of Knn classification or some potential problems. But before we continue, let's actually take a short break so that you can relax a bit. See you in a couple of minutes. Welcome back. So let's talk about some potential problems or limitations, so to say, of Knn classification. And let's say we have the following example. So same data as before, but now the first feature is one order of magnitude larger than the other one. So think about, for example, that here you're measuring like the age of a person, and here you are measuring, let's say, the American shoe size, which is usually a rather smallish number, right? So what will happen in this case? The point is, if you now compute, for example, Euclidean distance, you will see that if you are walking along this direction, the Euclidean distance might change dramatically, right? By walking along this direction, the Euclidean distance only changes a bit, right? So to make it more clear, think about here, this is even larger in the millions of, let's say. Then of course, changing here, change the Euclidean distance around the millions, but walking here only changed it a bit, okay? What it means for the actual decision boundaries is that they will look like this here, like these small stripes, right? Because again, walking along here doesn't change the distance too much, right? So meaning this sample might be a nearest neighbor of this one, right? It looks far away, but actually it's very close by, because here this feature has no effect. While this sample here has a very large distance to this one because we have such a big magnitude, okay? So we're getting these stripes if we have these different scales. And of course, this is not what we want, right? We don't want these stripes. They don't look like a nice generalization result, okay? So scaling is indeed a big issue of Knn classification methods, because the underlying distance also has this issue. But indeed, it's not just an issue of Knn classification, but in general, these different scales of features are something you have to take into account when doing machine learning, when applying machine learning models. And indeed, the solution to this, or one solution to this, is, for example, to do data normalization, data standardization. This is something you should, I would say, more or less always do when applying machine learning for some kind of new data set. So we want to do data standardization, normalization. And there are different ways of doing this. One is the so-called zero mean unit variance normalization, or often called the z-score normalization. So what do we do in these scenarios? Here we do the following. We compute the mean per feature. Okay, this is what you see here, right? Per feature, we compute the mean and we subtract from the data, and then we normalize it by the variance in this dimension. So what we get out here is essentially for every feature afterwards, we have a zero mean and we have a unit, so one variance, okay? So every of these features now is more or less like comparable, right? Zero mean and one variance. So data standardization is something you should potentially always do when working with machine learning models. There's another kind of normalization, which is often called like min-max normalization. What this is doing is it simply takes your data and, for example, it normalizes it in such a way that the domain is between 0 and 1, right? So let's say before your data was like between minus 20 and 35, min-max normalization transforms it that it becomes, for example, between 0 and 1. Okay? So note that this is different to the z-score normalization, which maps it to zero mean and unit variance. This here can still be outside the 0-1 interval, right? It can be some arbitrary domain. Here we parameterize the mean and the variance, while here we specifically parameterize already the data domain. It depends a bit on the application and the data, which one makes more sense. Here in this case, you specifically have to be careful when you have outliers in the data. So let's say you have one sample which is minus 20, but the rest of the data is, so let's say here's your data axis. You have one sample here, and the rest of the samples are here, right? Then 0-1 normalization would say, okay, this becomes 0 and this becomes 1, even though this is just some outlier, right? So actually you would prefer to have here most of your intervals, so to say, okay? So min-max normalization is a bit sensitive to outliers, but this is a bit better in z-score normalization, even though, of course, still not perfect, because the mean is also not robust to outliers. Anyways, so data standardization. This is something you have to take into account. In general, as I started with this video, look at your data first. See how the features look like, what is their scale, how do they behave, do they have some weird kind of outliers in the data, right? This is always what you should do first. Data cleaning, data preparation, normalization, standardization, getting rid of outliers, transforming it to the correct domain, for example, transforming centimeters and meters, for example. All these steps, this is extremely important to do before you actually start with the machine learning model application. Okay. So one other point I quickly want to mention here. So data standardization more or less also corresponds to, or can be thought of as applying Melanobus distance instead of Euclidean distance. So remember here the definition of the Melanobus distance. If this is the identity matrix, it becomes Euclidean distance. So you can think about using this matrix you put here, for example, like the variance terms, right? So which you here essentially divide by. So if you have here the variance terms squared, then this here more or less would do the normalization or the standardization inside the distance computation. So a z-score normalization plus Euclidean distance is more or less the same as doing Melanobus distance without a normalization, but using this kind of covariance structure, just as a small side remark. Okay, so this is something you should always take into account, scaling issues. And then there's a second point which specifically applies to Knn classification. With other models we later see in this lecture, might not have, at least not in such a strong degree, is a so-called curse of dimensionality. Curse of dimensionality, I give you here one point of view on this problem. There are many, many different theoretical results on this. Here I give you a very practical intuition what this means. So curse of dimensionality specifically relates to scenarios where the data itself is very high dimensional. And this could be, for example, again, this example that you have people and you want to classify or want to predict the income, let's say, and for every person you record many, many different features, right? Not just the age and the city where the person is living, but many, many different features. So we get so-called high dimensional data, many features, okay? So why is this an issue for Knn classification? Here's a simple example. So let's say you have even, let's say, a discrete domain, okay? So your domain is like 10 different numbers, 10 different categories, so it's not the age anymore, but some other discrete domain. So what you see is, if you now want to, let's say, cover the space, so to say, you need only a few points to do this, right? You see, for example, if you have n equal to 20 uniform samples here, right, most likely you will cover every possible position, right? So because you have here more or less like 10 different choices, and if you have 20 training instances, it's most likely that at least some of these will get one, right? Of course, it can happen that someone get 3, then some stays empty, but it's very likely that you can cover the full space, okay? So if you now go higher to 2 dimensions, let's say, right, you have here 10 choices and here 10 choices, so overall already 100 choices, you see that with 20 samples, 20 training samples, you only cover a bit of the space. So here, I guess, apparently it's 80%, right? So a lot of space is already empty, right? And of course, you can think this even higher and higher, right? So if you go to a 3-dimensional space, you have 10 choices, 10 choices, 10 choices, so overall 10 to the power of 3 choices, right? So then again, having 20 training samples, you only cover 2% of your space, okay? So simply speaking, one problem or one intuition of the curse of dimensionality is that the space becomes rather empty. Right? If you have a very high dimensional space, and of course you only have a finite amount of training samples, your space will most likely be very empty. And why is this an issue for Knn classification? The issue is because Knn classification relies on the idea that I want to find similar instances. I look at my neighborhood, right? What is similar to me? And if I have a new instance which is located here, and I try to look at my neighborhood, right? I see that the neighborhood is quite empty, or meaning all my neighbors are very far away, right? Again, think about like humans. If you compare to humans on the, let's say, genome level or on very fine-grained information, everyone is quite different from each other, right? We have all kind of different properties. We don't agree in every tiny detail, right? So the space, right, of different features we could construct is so big that if we then measure distances, everyone is very far away. Everyone is different. So the space becomes empty. Or simply speaking, also the nearest neighbors are pretty far away. So the meaning of a near neighbor doesn't make any sense in a very high dimensional space. To solve this problem, in principle, we can of course collect more data, right? If we collect more and more data, if we are lucky, then there is someone which is again similar to myself. But the point is, this number of samples has to grow exponentially, right? Because the space grows exponentially. It's 10 to the power of 3, 10 to the power of 4, 10 to the power of d possible choices if we have d dimensions. So we have an exponential growth in the space, so to say, meaning we need exponentially many data samples, which is not doable, right? The data cannot grow exponentially. We don't have the capacity to collect such data sets. So for high dimensional data, Knn might not be a good idea because we don't, or the meaning of nearest neighbors doesn't make any sense anymore. So later on in the lecture, in the second part, we talk about dimensionality reduction, where we can reduce high dimensional data to lower dimensional data to capture the most relevant information. And in this lower dimensional space, it makes total sense again to apply Knn classification, for example. But also in the next videos where we talk about decision trees, we see how we can also circumvent this issue of very high dimensional feature spaces. Okay, so one last point to this curse of dimensionality. There are also some kind of practical considerations, specifically also in the sense of applying Knn classification. So you have noticed that I talked about training a couple of times during this short video. Like we are training a model, and machine learning has some kind of training, and then we are applying it to new data. But in the Knn classification, we actually don't really have some kind of a training. So what does training here mean? And indeed, as I said, we don't really have this. So Knn is also known as a so-called lazy learner, because we actually don't construct a so-called model, what we see in the next video, what this actually means. But instead, what Knn is really doing, it's lazy because it waits until it gets the new test instance, right? Think about again how it works, right? Knn gets a new test instance, and then just when it receives this new test instance, it starts working, right? It looks at the neighborhood. Okay, so it's really lazy. It waits until it has to make a decision. Before that, it doesn't do anything, right? It's a lazy learner, okay? So why is this an issue? It's an issue because we don't really have now a compact representation of our decisions. Compact means we can't now easily make our decision, because what we have to do always is, at least in the naive implementation, we have to iterate through our data and see what are the closest neighbors, right? So this is the core idea. We get our query, we have to iterate through the data, see what is the closest neighbor, and then we have to make a decision. If we get a new instance here, we have to iterate through our data, see what is the closest instances, we do Knn, and then we make our prediction. So in the naive way, this is a very expensive approach. It requires O to the n operations, so n being the number of training instances. We have to iterate through all of these. So it takes time, and it's also memory consuming, right? Because we have to store all these instances. So this is actually rather expensive. Knn is rather expensive in the naive implementation. As a plus point here, and we don't discuss this in detail, there are some faster ways of doing Knn search, so like in KD tree, which however only also works in somehow low dimensional spaces, but there's also like approximate nearest neighbor searches. These could be used to speed up Knn classifier. They, for example, allow you to almost constant complexity of 1 to approximately compute the nearest neighbors, and since approximation is usually good enough, you can also speed it up. But again, this is one important limitation of Knn, since in the traditional way it's a lazy learner, it's rather expensive to do like later on our predictions. And in the next video, decision trees, we see one way of circumventing this issue. Okay, so this is already then the end of this first video. So what did we learn? We learned about this Knn algorithm, which we can use for nearest classification and regression. We look at our nearest neighbors. You should also remember this train validation test split. Training data, where we actually train our model, which we use as a base for the Knn classifier. Validation, which we then use to evaluate what is the performance on this validation set, and we can use it to tune our parameters, which K do we pick, and then test data finally, which we can then use at the very end to report the performance of our model. Okay, so train validation test split, extremely important. We talked about different measures, accuracy, precision, and recall, so how to evaluate the performance of specifically classification. We talked about distance metrics, which we can use inside of a Knn classifier, Euclidean distance, L1, L infinity norm, for example. And last but not least, we talked about some limitations, specifically the curse of dimensionality, which you always have to be careful with when using machine learning. What is your data space? Extremely high dimensional data is an issue, specifically if the number of features might even be larger than the number of training instances you have, then it becomes very, very tricky to do machine learning. There's some special research in this direction as well. Okay, so far that's all on the Knn idea. I hope you got a good idea how machine learning can work and what it can do. As usual, feel free to ask your questions online, and we will see us in the next video. Bye bye.